So good afternoon, dear students. Can you hear me? So can you hear me?
Yes, hocam. Good afternoon.
Okay, good afternoon. So okay, then let's start. Okay, I'm going to share the screen with you, and we'll continue with our program. Okay. So we started to talk about to discuss the topic of velocity, and in our last lessons, we were on that point. We were talking about the graphical velocity analysis or relative velocity method. And as you remember, we had a crank rocker mechanism, and in this crank rocker mechanism, we were interested to define, to calculate, to the velocity on the point A, B, and any point on the coupler. So, and we said there are some givens, and considering or taking into account the givens, we are able to calculate the velocity on coupler of any points or the points B, which is the shared point with the B0B and the rocker and the coupler. So, and then we said mainly if you have a mechanism somewhere to design, mainly we know the A0, the length here, the crank length, and also the RPM. Actually, the dimensions are also known. So if we make velocity analysis, dimensions are known. That means all the lengths of the links and the starting point, and that means the geometric parameter. All of them are known. And one thing is also known. This is the rotation of the crank. That means A0, this is rotation. Rotation means RPM. And let's assume here that we have the AO. So the length AO is known, and also the rotation and RPM is equal, let's say, 200 RPM, and when we know the rotation of the A0A, then we can calculate the angular velocity. So the angular velocity is equal 2 times pi times n, and since this is the per minutes, and we have to divide the 60 in order to calculate in meter per second. So then if we here if we continue here, so omega is equal, so 2 times, let's say 3.14 times 200 200, so over 60 and 60, so 260. Okay, this is and here we have 1, here we have here 3, and this is around, let's say 7, so 21 point, let's say 5 around radian per second. So nearly, I didn't calculate it exactly, but 20, let's say 21.5 radian per second. So that means we know we can calculate the angular velocity omega. If you know the angular velocity of the crank, so we can calculate also the linear velocity VA. VA is equal, as we know, this is the length here, A0A, A0, A times omega, you know that. So A0 is, let's say, given, let's say the A0 is, A0A is, let's say, is, as a length is given, let's say, 20 millimeters. So then VA is equal 20 times 21.5. This is millimeter per second. So if you calculate in that way, it's millimeter per second. This is so nearly, let's say 400. So 400, 5, so around 405 millimeter per second, millimeter per second. So that means we know actually the velocity of the point A, tangential velocity or linear velocity, and we know our interest is to calculate, as you see here, the velocity of the point B. We know from the equations how it is by the calculation of the relative velocity. VB is equal VA plus VBA, and we know the A. Okay, A is known as magnitude and also direction, because we know the direction of the, if it is turning, the A0, A is turning clockwise, so the direction VE is like this here, we see VE perpendicular to the A0A, and we say this starting from one point. Let's say this is the point we started, and we can draw a parallel line to the VA like this. So, and we know also the end point of that. This point is also known. So that means we know VA completely, direction, magnitude, since everything. But we are interested to calculate the velocity of the B, or velocity B about the A, tangential velocity. So we know the direction of the velocity of B and velocity of BA. The velocity of B, direction-wise, must be also perpendicular to the B0B, like this, and perpendicular, this is the VB, but we don't know the magnitude, we have to calculate. So then I can draw a parallel line, let's say from the point of here, of the, let's say, let's assume, say O, from point O, and this is VB. But we don't know the actually don't know the magnitude. Therefore, this is a line going like this. So we know also the direction of the BA. So BA must be perpendicular to the line AB. So then here the VBA, and we know the direction, and we can draw a parallel from the point where we had the end of the vector VA, and another parallel to the VB here. So and then these two lines, let's say this is the L1 and L2, are crossing here on that point, and that means this is the end of the vectors VB and VBA. So graphically, we calculate, we find the velocity VBA and VB, and if we consider as in form of vector, normally VB is equal, you see VB is here, let's use the laser pointer. So VB is equal VA plus VBA. VA plus VBA. Okay, this is also correct. So then, so how can we calculate the magnitude VBA and VB? So we can select the scale for the vector VA. Let's say this is the 5 or the 50 millimeters we use here. And if it is 50 millimeters, and if we draw correctly the lines L1, L2, and at the end the crossing point here, and we know the length here, and if we measure the length and multiply with the scale factor, and same for the VB, and we can actually calculate the magnitude, also the magnitude of VB and VBA. So this is the way actually how can we calculate it graphically, the velocity of the point B, which is the crossing point of or the connecting point of coupler and rocker, and also any other point on C, say on the coupler like C, for example. And we know also that any point on the A0A is traveling on a circular path, and the same for the B0B, but any point on the AB is not like this. It is undergoes a general plane motion. So therefore, it is not so easy like any point of or on the A0A or B0B. So if we, for example, are interested to calculate the velocity of the sea, we have to write the same equations and act accordingly. Like we say, let's choose another color here, maybe this one, okay. So, and we can write VC is equal, so we know the A, again we write VA plus VCA. VCA, you know, this is the relative velocity, and that means C is turning about the point A. So, and this is like this, so this is the line. So this is the line here, and we know the VA. We have already calculated. We know the direction of do we know the direction of the VC? So we know the direction of, we don't know the direction of the C, but we know the direction of the CA must be perpendicular to that. Must be perpendicular. But we can also know the direction of the C. We can easily calculate. We will learn it in the following part of the lessons. We have to find the instantaneous center, turning instant center of the AB, and we will learn that. And instant center is like this. If we expand this line and this line here, they are crossing somewhere here, and we have the instantaneous center, turning center somewhere here, and then the point C is turning also at that moment, at that time, at this instance, around this here, the instant center EC, we will learn in the following part of the lessons, and must be also perpendicular to that. So this line, I mean the direction of the velocity of C. So again, using the we know that we easily find the directions of the point of the velocity of C and the direction of the velocity C about A, and we know the directional magnitude of the VA, and we can calculate graphically like we did for the point B. Okay, let's have an example here. So the crank and the connecting rod, this is the crank here. Let's use the edge, okay. This is our crank here. You see here, this is the crank, and this is the coupler here. Our coupler here. So, and this is the sliding part, or let's erase it. So use another color. I'm going to use another color. So this is the so this is, let's say, this is our coupler here, and this is the sliders. We have to also indicate the slider. This is the slider. So okay, so two members, the moving, the crank, and the coupler and slider. So what is given? The crank and the connecting rod of a theoretical steam engine are 0.5 millimeter and 2 meter long. That means, let's write it here. It's already written, but here this is the 2 meters here, 2 meter, and 0.5 meter is the crank, 2 meters is the coupler. Okay, given. So those are the givens. And the crank makes 180 RPM. So this crank, that means N is equal 180 RPM, 180 RPM, in the clockwise direction. Okay, this means clockwise means so in that direction. So it is turning in that direction, clockwise. Okay. So in that direction, when it starts turn 45 degrees from the inner dead center, that means this is, the inline mechanism, inline slider crank mechanism. It seems so like this, inline slider crank mechanism. So inner is saying that, so inner dead center. Inner dead center means, what is that? So inner dead center means this line here, and the angle from here is the 24 degrees, so 45 degrees. This is the position of the mechanism for this instant. And so okay, what is the question? Velocity of the piston. So we have to calculate the velocity of the piston P here. So that means VP is equal question mark. We have to calculate. This is the angular velocity of connecting rod. This is the connecting rod here. So the angular velocity of, that means angular velocity of VBP. That means P is about the point, B about the point of P. So also has to be calculated. So then the velocity of the point A on the connecting rod, this point A here, velocity, that means VA has to be also calculated, also question mark. So, and this is VA is 1.5 meter from the gauge pin. That means from this pin here. So this distance is from PA. That means here we can write PA is equal 1.5 meters. So in total, the coupler is, that's PB is 2 meters. PB is equal 2 meters. 2 meters. So you know that. Okay. So the next one is the position and the linear velocity of any point G. This is the here. This must be G here somewhere. Let's say the G. We don't know the position for the time being. Any position and the linear velocity of any point G on the connecting rod. On this must be on the connecting rod. A rod which has the least velocity relative to the crankshaft. Least to the crankshaft. Okay, so let's start from the first one. Velocity of the piston. Velocity of the piston. So you can easily estimate that the velocity of the crank is not a big problem. Velocity of crank. So we have to calculate first of all the velocity of the crank. Why? Because we know the length and we know the RPM actually turning. So like we did in our previous part of the lessons. So omega, let's say the crank or OB is equal, 2 times pi times the rotation, that means the RPM, and we can calculate it 2 times, okay, let's say 3.14 times 180 times here 180, so over 60, because we have to convert into the second, so 60. And if we assume that the pi is nearly 3, and 2 times 3, it makes, okay, let's, for the simplification of the simplifying of the calculations. So it makes 2 times 3, 6 times 180. This is the RPM over 60. So then let's take out or 6. Here we have 1. Here we have also 1. So, and this is equal. So this is equal nearly, let's say, 18 radian per second. This is the angular velocity, omega OB. So 18 radian per second. Okay, we know the angular velocity of the OB. So how can we calculate the tangential speed of the point B? We know that from previous explanation. So VB is equal, VB is making a circular motion. I mean, it's turning like this, this path undergoes circular motion, fully circular motion, pure circular motion, like this. So then VB is equal the length, the crank arm OB times omega OB, and VB is equal from here. VB is equal, since so OB is 0.5 times 18, nearly, of course, and this is equal 9 meter per second. 9 meter per second. So we know the we know the speed, linear speed of the point B. Let's use another color here, like this here. Okay, VB. So the direction, since it is turning the clockwise, so it must be in this direction and tangent to this circle here, tangent. So this is and perpendicular to OB, the linear motion. This is the speed B, linear speed or tangential speed of VB. We know the magnitude, we go the direction, since everything we know. Everything is known. So, and let's come to the question. So velocity of the piston. So velocity piston is here, P. So we know the direction of the velocity piston. So we can write following. We can say V piston is equal. V piston, let's say that in that way. V piston is equal. We know which one we know. We know the VB. It's also on the same let's say the link. B and P are on the same link. So that's the reason why we are writing these equations. And VP is equal VB. VB is known. We know we have to calculate it, plus V B over P, about the P. Sorry, about the P. So this is the equations. So we know if we consider that. So what we know here, we know the direction and magnitude of the VP, and we know direction of BP, and we know direction of the VP. So the direction of VP must be like this, yes. So where's that? Okay, let's use the red one because I'm losing that. Okay, so the direction is like this here. So this is the direction. So let's say the direction of VP, it has to be parallel to that. Okay, and I select any point here, any point, let's say the O, and I draw the velocity of the point. I bring the velocity of the point B here on the in the same direction. So this is the must be VB. So this is the must be parallel to that. So and this is the VB. VB. Okay. I know the VB completely, magnitude and direction. I know the direction of the P. This must be VP here. VP. I know the direction, but I don't know the magnitude. And I know the also magnitude direction of the here VBP must be perpendicular to the line, to the BP. So perpendicular to that line, I draw a line from here, from the end of the vector VB, a perpendicular. So it must be a perpendicular line. This must be perpendicular to the line PB. So then I have here VB, and this must be V. Here must be BP. This is the value of VBP. So I have the vector polygon here. That means VP is equal. I was interested to calculate. I'm calculating the speed of the VP, linear speed or tangential speed, or the speed of the VP. So VP is equal VB plus VPB. VB plus VBP. So if I use a scale, because I'm working as graphically, use a scale, and let's say VB is 4 centimeter or 40 millimeter. So after drawing the vector triangle, so then using the scale, I can calculate also the magnitude of the vector VPB and VP. So the second question is angular velocity of the connecting rod. So angular velocity connecting rod, which is the connecting rod? Connecting rod is PB or BP. So I have to calculate, or we have to calculate the angular velocity. So I know the what is it? My cursor. I lost my cursor. I know the linear speed of the VBP, isn't it here? Calculated already, VBP. So let's write here VBP, VBP is known. Why it is known? Because you calculated here, VBP. VBP is known. Okay, since I know the VBP, and I know also the length of the BP, so then VBP is equal, actually, VBP is equal the length BP times omega BP, B about the point P. So what is known here? Here is known, the length is known, and VBP is known, and I have to calculate the omega BP. So it's also possible here to calculate. So we know V omega BP is equal, angular velocity is equal, so VBP over BP. So BP is known, the length. VBP is known. We calculated already from this vector triangle using the scale, and graphically we calculated. So the second part is also finished now of the question. So that means we calculated the velocity of the piston, and we calculate also the angular velocity of the connecting rod. So the next one is the velocity of the point A on this coupler A. Here, velocity on this coupler A, which is length is 1.5. This is the same like the B. Yeah? So 1.5. Because we have this velocity here, we have this triangle here. O from the point of VB, VBP, and VP. So the relative velocity, that means BP or EP for the point B, must be on the same line. So then we have to actually calculate the so we can calculate the value of the E about the point for this instance. E about the point P, and this is same triangle. So the length and this is the okay, is that we okay, we know the length of the point. We know the length of the velocity of the point P, and we know the length of the point of the E must be perpendicular to this line, and this is also known. And using this relation, we can calculate the velocity of the point A, like here. You see then, let's use the laser pointer here. So our VP is already here shown, and this is the VB, the linear velocity of the point B, and this is the VBP here. So, and then we can, using these vector relations, we can the relative velocity. You can calculate the relative velocity here. What's the relative velocity? E over the P. This is not a, not a big problem, because we know the angular velocity of the BP. That means the B about the P. And since we know that, and we know the length here, we can calculate the linear velocity, and linear velocity we can draw like this here, and this is the relative velocity from E to the B, and we can draw for same for the G. The conditions were what was the question for the G. Piston linear, so this first part of the question, position and linear velocity of any point G on the connecting rod which has the least velocity relative to the crankshaft. Velocity relative to the crankshaft, that means must be the smallest. Huh? So here, the velocity, this is the moment VE is equal VE. Okay, VE we can calculate. VP also, VE we can calculate also in the same way. By sorry, one moment. So okay, VBP, okay, good. Millimeter, okay. So let's check once more the position and the linear velocity of any point G on the connecting rod which has the least, that minimum velocity relative to the crankshaft. Relative to the crankshaft. So relative to the crankshaft. So relative to the crankshaft, actually relative to the point P, relative. So relative means must be on the same line, and this is the length here. If we use the graphic, this is the length. This is the relative velocity. We can find somewhere here or there. It depends. So it is, so how least velocity, but how much we don't know. So therefore we can let's say assume that this is the smallest relative velocity here, and therefore if we indicate the g somewhere here, and we can drawing this vector here, we can calculate the vg from this graphic using the scale, and also we can calculate the relative velocity here, vg about the point P. Okay, this is the graphical way how we calculate actually the relative velocity. So I have another example here. Again, for the relative velocity, to calculate the relative velocity. What is given here? Let's say we have a triangle like this, and in this triangle we have the linear velocity VA and VB, and we are looking for the relative velocity of C. So we don't know, but we can write the equations like this. If we know the VA, for example, we can write VB is equal VA plus VBA for the relative velocity, or VC is equal VA plus VCA, or VC is equal VB plus VCB. So both of them possible. And in order to calculate it, that means, so from the given, we know the direction and magnitude of the velocity of the point A and B, VA and VB. So again, we can use select a point here. Let's use the pencil. So any point here, let's say the O. So we can select arbitrarily. So then we can draw the speed with a scale, of course, using a scale, VA. So this is the VA here. So let's say this is the VA. Okay, VA. So because we know the VA, it's completely known, direction and magnitudes wise. And we can draw also the VB. So this is the VB here. And we know also the direction, VA is known already, direction and the magnitude is known. And also the direction magnitude of the VB is known, like this here. So VB. And we can draw also the VB here. Where's the VB here? You see, same direction, same magnitude, VB. Okay, this is the VB. And we know the direction only of VBA. V, you see here, this VB about the point A. This is the VBA. So VBA relative velocity, VBA is relative velocity. This is the velocity of the point B relative to A. That means looking from the A, this is the rotation. It is a point B is turning, we assume turning about the point A. So it must be perpendicular to this line, to AB. must be perpendicular, the direction perpendicular to the AB. And we can draw it like this here. This is the line here. Let's use another color here. So let's use this one. This is the line here, perpendicular. No, perpendicular to that. This is perpendicular to AB, huh? AB. So perpendicular. So then we have the polygon here, the vector triangle. Let's use this color here. Okay, and this is the equation actually. VB is equal. Let's see, VB is equal VA plus VBA. So VBA. That means we calculated already the relative velocity from the point B about the point A. So now we are looking for the VCB and VC and VCB. So for that, if we come to the point C, for example, here, the point C, what is given for the point C? We know let's use these equations here. We are interested to calculate the relative velocity of the linear velocity of the point C. VC is equal VE. VE is known already. We know the VE is known, direction known, and magnitude known. And plus VC is equal VA plus VCA. VCA, C about the point A. So C about the point A, this is relative speed must be perpendicular to the line of AC. Must be perpendicular to the line AC. And this is the line here. Looks AC, perpendicular to the line AC, perpendicular to the line AC. And we draw a line like this here. This is the line here we draw from the end of the vector of VA, so here in that direction, and this line is crossing a line somewhere here. This is the VC. We know the VC. Do we know the VC? No, we don't know the VC. We know the direction of the VC. Or we don't know also the direction of the VC. We don't know anything about the C. But we know the direction of VCB. VCB. C about the point B. The C about the point B. We know the direction. This is VCB. VCB. C about the point B. And it must be also perpendicular to this line. So, and if you draw, this is, let's say this is the line. This is the line, line 1, L1, and this is the line 2, L2, and this is the line L3, L3. This is the L3 here. Huh? So, where is it? Here. This is the line L3. So, we know this line. It must be perpendicular to the line BC. So, and these two lines, this L1, AC, where is it? So the other line is here. So, okay. Okay, this is the line L1. L1, this is the L2, and this is L3. So the crossing point of L2 and L3 here is the define the end of the vector of BC, and then we have here the relative velocity, the velocity of the point C here, VC. So you see here, if we check these triangles of the vectors, we can write here, for example, VB is equal, like this, VB is VA plus VBA, or if you write VB is equal, for example, or VC is equal VA plus VCA, VC is equal VA plus VCA, like this here, or we can write VC is equal VB plus VCB. VC is equal VB plus VCB, or VC is equal VA plus VCB. So that means if we know the linear velocity of 2 points of any member, we can calculate the linear velocity of any points on this member, like C here. So we didn't know anything about the C, whether direction nor the magnitude, but we know for the point A and B, the linear velocity was given. That means the direction and magnitude. So using these givens, we are able to calculate the linear velocity of the point C. So, okay, do you have any question? So if not, then we make a break, 15 minutes, and after 15 minutes, we start it again, okay? Okay, let's start. So, can you hear me? And can you see the slides?
Yes, Hocam.
Okay, thank you. So, let's continue then. We have an example here, and given is the offset slider crank mechanism, and also the dimensions here, like the crank length of the crankshaft, and the here and the length of offset and the length of coupler and so on. So the question is, the 250 millimeter crank is rotating. This one here. Let's show it. So this is the crankshaft here, 250 millimeters. Okay, is rotating at 300 RPM. So 300 RPM. The length is 250 millimeters clockwise, and determine the velocity of the piston. So the piston, this is the piston. Let's use another color for the piston, like this here. This is our piston here, and we have to calculate the velocity of the piston. Okay. So we learned actually in our previous discussions that if we know the RPM of the crankshaft, let's say this is A0 here, A0 point A0, and this is the point A here, and let's say this is the B point B here, the joint coupler to the piston. This is the piston here. So the question is, how can we calculate the velocity of the piston? That means velocity of piston, and let's say this is the P, our piston here, P piston. Okay, so we know for the four-bar mechanism the relative velocity equations. That means we can write VP is equal like we did in the previous example, VA on the same, VA is on the same link, I mean on the coupler, VA plus VPA, that means P relative to A. So in these equations, what is the question? Question is the VP. So how can we calculate, determine the velocity of the piston? So of the piston, okay. So the velocity of the piston, how can we determine the velocity of the piston? That means this we have to calculate. And we know the VA is known. So direction, magnitude. So magnitude, let's say the magnitude is known, we will calculate, and directions also known, direction, so also known. And for that, VPA, we know only direction. Direction we know, but magnitude we don't know. The magnitude we don't know. Okay, so we said we know the magnitude and direction of the crankshaft. So how can we calculate that? Actually, we know for the crankshaft, we know the length A0A is equal 250 millimeters. 250 millimeter already given. So, and the rotation is also given. 300 for the crankshaft is N is given. N is equal 300 RPM. 300 RPM. Okay, is also given. So then we have to calculate the VA. So VA is equal, we know, A0O, A0A, the length, times angular velocity of the crank. So this is known, and angular velocity we can calculate in that way. Omega is equal, like we did, 2 pi n, and this is equal 2 times, let's assume that we take it as 3, so times 3 times 300 RPM, 300, or 60 because we have to convert into the second. So then, okay, take the 0 from here, then from 0 here, and the 6 we have here 1. Here we have in 30, we have 5 times 6, and this is nearly 30 radian per second. So 30 radian per second, the omega. So then we can calculate here the VA is equal, the length is 250 millimeter, 250 millimeter, and the omega is 30 radian per second, and this is equal. So mm, 7,500 millimeter per second, or 7.5 meter per second. So this is the speed of the crank, the VA at the point A. So, and now we already know the speed of magnitude and the directions of the VA, and then we can, using the graphical way, we can draw the speed of the VA. This is for this position must be perpendicular to the A0A, like this here. So in that direction must be. Since it is turning clockwise, it is turning clockwise. This is the VA. So VA. So we know the magnitude and direction, and we know the also direction of the VPA, direction VPA A relative to the B must be perpendicular to the line AP, like this here, must be perpendicular to this line. So if we draw a perpendicular line to that from the end of the point of the vector VA, like this, okay, perpendicular. So And what is the direction? We know also the direction of the point of the piston. You know the VP direction is like, I mean, it moves so like this. This is the direction of that. You know the direction, and we have also draw a parallel from the point A to the direction of the VP like this. So this is parallel to that. So the crossing point gives us the magnitude of the VP and VPA. So this is the VP here, VP, and this is the VPA, VP relative to the point A. So, and using a scale, because we know the VA, let's assume that VA is maybe 50 millimeter. We take 50 millimeter for the VA. We know the magnitude of the VA, 50 millimeter, and using this scale, we can calculate also VP and VPA. So in that way, we know the VP. I mean VP, the magnitude and direction of the linear speed or velocity of the point P, piston actually. So you see, it's not so complicated, quite easy. Okay, this is the way, this is the graphical way we use to calculate the speed of the piston. So another example here, we have for saving machines. You see the saving machine here, but the mechanism is not given, so we have to show that this is the mechanism. This is the coupler, for example, here. So this is the coupler, like here you see. So, and this is the sliders. You can see this is the slider here. You know, going up and down, So we know this going up and down, So like this, okay. Linear motion. And this is the coupler, and the eccentricity here is shown in millimeters. Let's use this color here, and this is this one here. The eccentricity. This is the crank length of the crank, 15 millimeter. That means this is a slider crank mechanism. Offset slider crank mechanism, slider crank mechanism, like this. So we can show like this here. This is the pivot point rotating around this point here. So, and this is the eccentricity here, length of the crankshaft here. So, and here we have the connections like this, and this is the coupler like this here, and we have here the joint again. So I have to, so maybe I have correct it a little bit here. Okay. So this is the coupler. Also not correct. So I'm trying to draw as it is shown in the figure. Okay, like this. This is the coupler here, and we have here the connecting point, and there is a slider here moving up and down. Let's show it as a mechanism like this here, and this is the line along moves the slider, and here we have the offset 15 millimeters, 15 millimeters as it's shown here. No, 8 millimeters, sorry. So it's 8 millimeter. How to correct it? So then here's again. So the 8 millimeters. Okay. So what is the question? This the saving machine linkage determine the linear velocity of the needle. So this is the needle, huh? This is the needle here shown in blue. So we have determined the speed of that. As drive wheel is rotating at 200 RPM counterclockwise. So counterclockwise, that means in that direction. Huh? So counterclockwise. Same like we did in previous example. Easily calculate the speed of the point. Let's indicate the points here. This is the here A0, let's say, or A, B, and C. Let's say here the C. So, and we can calculate the point, say, velocity of the VB. Linear velocity B is very easy because VB is equal omega times, or that's not right, is equal, the speed is equal, so AB times the length AB times omega, the length. Omega we can calculate, RPM is given already for the crankshaft, so RPM. Omega is equal, N is given, here N is equal 200 RPM, 200 RPM, and this is the N given here, counterclockwise like this. This is the N here, okay. So then omega is equal here, so AB is 15 millimeters, so 15 times omega is, so 2 times pi times 200 over 60, because we have to convert in a second. So then at the end here we have, let's assume that the pi is 3, and then it is equal, so 15 times 2 times 3, 6, okay, times 200 over 60, and then we have here 0 take out, here we have here 6, 1, and here also 1, and we have here 20 times 15, so it is equal how much? 300. No, this is VB. This is VB, sorry. 300 millimeter per second, or 0.3 meter per second. So, or this is equal 0.3 meter per second. So we know the magnitude, we know the directions. Direction counterclockwise must be, let's use the another color for the vector polygon, like this here, and this must be perpendicular to that, counterclockwise like this. This is the, so perpendicular to AB. This is VB. So then we know the, let's draw the polygon, vector polygon here somewhere, and this is our, let's say VB is given. VB is given, and the direction of the VCB, so that we didn't write the equations. Okay, let's write the equations. VC, the needle, the speed of the needle is equal VB plus VBC to VCB, sorry, VBC, VCB, okay, VCBC about the point P, okay. And we know the direction, magnitude of VB, and we know only the direction from VCB, and we know the direction of VC. So direction of VC is like this here, VC along this line. So I have to change a little bit here because drawing will be not so easy. And here, take it away, okay. So let's say this is also not correct. I have to change it a little bit. So this is also not perpendicular to that. Must be perpendicular. So then use that. Okay, here must be perpendicular like this. Okay, this is VB. Okay, then we can draw the VB like this here. This is from a point, let's say the arbitrarily selected a point. This is the VB. So VB, and we know the direction of the VC direction must be parallel to that. So, and this is the direction. This is vertical here like this, parallel to the line part of the piston or slider or needle. So then we know also the direction of the direction. We know also direction of the VCBC about the point B must be perpendicular to that here, to the BC must be perpendicular. So we can draw a perpendicular line like this. So this is the L1 here. Let's say the L1. We can draw the L1 here from the end of the point of the vector VC like this. This must be also parallel. Let's say the parallel to that here, L1. This is L2. Let's say here L2, and we have here VB, and this is the VC here, VC, and this is VCB. This is VCB. So that means VC is equal VB plus VCB, and using a scale we can easily calculate the magnitude of the needle. And you can do it for each position. I mean, you can calculate it for each position, turning 200 RPM, turning by the speed of 200 RPM. It's possible. So another example is so the 12 millimeter crank is rotating at 1200 RPM. So this is the crank here. Let's use it. This is our crank, but use the another color here. So the crankshaft, our crankshaft here is turning. So it's turning. What is the RPM here? 1200 RPM. Rotating counterclockwise. So the counterclockwise. So we have to also show what's counterclockwise. That means turn in that direction. So counterclockwise. So and clockwise. Determine the velocity of the 45 millimeter link. Where's that? This is here, 45 millimeter link. We have to determine the velocity. That means the velocity of the point A. So let's write the points here. This is the A, and this is here. Let's assume this is the point B, and this is the point C here, and this is the point D here. So that means so VC is the question mark. We have to calculate that. We know all the geometric dimensions like the length of the crank and coupler and the rocker and all those things. So we know the speed of the crank. This is 1200 RPM. So how can we calculate the VC? So as we discussed in previous lessons, we can easily calculate the speed of VB. So the VB is equal AB times omega, and omega is given already. So omega is equal here to pi times 1200 and 1200. So over 60, converting into the second and so on. And we can calculate the VB, and we know the direction of the VB, and we know the direction of the VB, and we have to calculate the VC. Okay, we know the direction of the VC, so using this, we know the direction VCB. So VCB is like this here. So we have to think direct connections here. This is the line here, VCB. So coupler can have this shape, but doesn't matter. This is the line, the important for us. So then using these equations, so here VC is equal VB plus VCB so VC is equal VB plus VCBC about the point B. And then, VB is known already, direction magnitude. We know the direction of the VC. VC direction, it must be perpendicular CD. And we know the direction also VCB. It must be perpendicular or perpendicular to the CB. So using this vector triangle, so vector relations, we can, and the scale, of course, we can easily calculate the VC and VCB. So I will not calculate into detail. So let's come to the point on a floating link. There's a point here indicated with X, like you see here. Let's choose the, okay, yes. Or use another color maybe. So this is the X value. X here, we are interested to calculate the speed of any point on the coupler, X. So, and it consists of, let's say the Vx consists of three components. Sorry, the Vx we can write Vx equal this general formulation. Vx is equal Vi plus Vxi, or any point V, if we know the Vx, or another point for Vg, for example, Vx Vg J plus Vxj. So X about the point J. So how can we do that? So velocity of point G and H. So G and H, G and H can be readily determined. We know that, we learned already velocity. So direction of the motion of G and H are known. We know the direction of H and G. So, and the direction of the relative motion of H relative to G is also known. H relative to G, H to G, or G to H. Velocity of point X is more difficult because the direction of the motion is not obvious. We don't know the directions. Need to use simultaneous vector equations to determine the motion of characteristics. So needs to use simultaneous vector equations to determine the motion characteristic, like this here, like we already show here. So there is an example here, and you have to work on that. This is homework for you. You have to work on that. The point X, we are looking for the velocity of the point X. So the 12 millimeter crank is rotating at 1,200 RPM counterclockwise. Determine the velocity of the point of interest X. So the point X has to be calculated. This is homework you have to do, Okay. Another example here. The 12 millimeter crank is rotating at 6 RPM. 12 millimeter, you see here, this is the, let's choose that. So this is the crank here. 200 millimeter crank is rotating at 600 RPM, counterclockwise, against in that direction here. So in that direction, counterclockwise, that means in that direction. So this is N is equal 200, sorry, 600 must be, sorry for that. 600 RPM. 600 RPM. Okay. So determine the velocity of the 45 millimeter links and the slider links. So determine the velocity of, let's say, the point. Let's write the point here. A, B, and C, and D, and A F. Let's say the point F. So we have to determine the velocity of the point. So VC is equal question mark and VF is equal question mark. So you have to determine that. So this is also homework. You can do that. Or you can, of course, you can calculate the VC, VF, VC, VE, VF, also VE. So VE is equal question mark. So you have to calculate that. So we stop here for today. And next week we will start from here. And we finish the velocity and we start the acceleration, the part of the acceleration, calculation, the acceleration. So any question?
Yes, Professor, I have two questions about last homework, the previous homework.
Okay, I'm listening.
Okay, can you please open the file?
Sorry, what? Can?
The previous homework, I have two questions in it. So can you please open the file?
Open which file?
Of the last homework, doctor.
Okay. Which one?
Okay, number 9.
Yes.
Okay, in the questions it said that theta2 is given while it's not given in the problem. So how can I solve this problem?
So theta2 is given. Theta2 is the angle and driver angle. We use it as driver. So you can use you can increase the theta2 1 by 1 or 5 by 5 or 10 by 10 in order to complete the 360 degrees.
Okay, I can't understand.
So you have to turn the link AB. Okay. This is a crank, This is a crank. So you have to turn this AB and from, let's say, from the counterclockwise or the clockwise. It depends what is given. I don't know what's given here.
Okay, but the initial position is not given.
So you can start from the 0. It is free. You can start from the 0. Let's say from 0 from here. Let's use the moment. Let's use the. I cannot. Okay, let's wait a minute. So you can start from so you can start from 0 and here like this and turn counterclockwise or clockwise or counterclockwise in that. So you can give the theta 10 by 10 or 10. When I did it 10 by 10 by 10 is not I mean it is enough. So 10 degrees and later the first step, second calculations 20 and like if I can write here 10, so then 20 and then 40, so sorry 30 until 360. Okay,
so the answer will be like a table or graphs. Is it okay?
You have to calculate and show the graph here. Which type of with the graph drawing by the point P.
Okay, thanks, Professor. Problem number 8. I have another question, Nit.
Okay. Which one?
Number 8.
8.
Yes.
Okay.
In the 4-bar mechanism, L1, the value of L1, the length L1, how can I calculate it?
Where is the L1?
Which is a vertical,
displacement. You mean this one here?
Yes.
You mean this length here?
Yes.
Okay. Let's see what is given here. So 180. So I think determine the displacement of the bottom of the tire if the upper control arm rotates. This is not given, huh?
No, it's not given, but
I
and
forget
so
it maybe.
the problem can't be solved.
So maybe I forget it. So let's see that whether I can find it. So let's okay, where is it? So okay. So this is not given.
Okay, so Professor, how can I solve the problem? Because the formulas for this 4-bar mechanism needs the length of L1 to be given.
Let's check it. So what is given here? So the angular analytical determined is analytically determine displacement of the bottom of the tire if the upper control arm rise. Hmm, 120. So you can select it. Actually, you can select it. This is 254. This is 200. This is 400. So so then it is. Let's take it 350. Huh?
350. Okay.
Yes, 350. Huh? I am right. Also 350. But you can. 350. You can select it. Huh? You can say I select 350 or something different.
Doctor, how can I select it? Also, I don't have the initial position of the links, the setters. I don't have the angle. So how
Initial
can I select
position
it?
here. Sorry, initial position is the 0 here. The crank, check the crank key.
Okay.
This is the 0. Yeah.
Okay. Okay.
You turn 20 degrees clockwise, and then you calculate it. Okay.
Okay. Okay.
So, any other question?
Thanks, Professor. I
Okay.
will submit my homework today because I didn't submit it because I have these questions and I sent a mail for you, but maybe you didn't see it. So I will submit
Okay.
it today.
It is okay.
Okay, thanks, Professor.
No problem. Okay.
Thanks.
So, another question? So, I'd like to share some information with you coming from the university for the students finishing these semesters, has finished the BS and bachelor in this semester. They have an announcement about the master science. So if anyone from you interested to participate to the master program, you can read the advertisement of the university about the master program, which is published by the institute responsible for the master program from our university. Okay. Any question? If not, I would like to say bye-bye for today. Huh?